so long we had been studying systems without the control input. So we are studying systems, unforced systems, which are also called homogeneous systems. So they are the systems where we were not considering the BU part, only x dot equals to ax, and we studied various um, like we analyze those systems in different manners by understanding the properties of A, the mathematical properties of the A matrix related to the state space, like the rank, the range space, null space, all these things. So these ideas will now get extended when we introduce the control input in picture. So the mathematical ideas will remain the same, and with the help of the control input coming into the picture, we will try to discover more features or more properties of the system. So with the control input in the system, the first feature or the first property of the system that we would be interested to understand is the property of controllability and reachability. So what are these? So let us go through the definition first, and then we will understand what exactly it means. So reachability is defined as this. So a state x1, so uh, in a particular state space, so this may be a particular state space. Suppose this whole screen is a state space. So you have a state x1 here. So we need to reach it in a time t1. The state x1 is reachable at a time t1 if for some finite initial time t0. So you start it's like you have a time axis here, and maybe it's a scalar. If you suppose it's a scalar, then you are trying to reach from some initial state x0 xt0, which is 0 here actually. So you are trying to reach from 0 to some state in this time. So this may not start from 0, so this can start from some other time instance. So let's see. So like from here to here, perhaps you are reaching. So you're reaching from 0 to x1 here. So this is a simple scalar case, but you can understand that if it is a high dimensional case, then you are starting from some point. Suppose this is the origin of that space, and in some time you would be reaching this point x1. This is our objective. So we are trying to see whether we can satisfy this objective for with the system that we are having. So that is defined formally like this, that a state x1 is reachable at a time t1. So the time is also mentioned here. If for some finite initial time t0, which is of course less than t1, there exists. So this symbol is a there exists. This symbol is like when you speak, you speak it like there exists. So the initial time t0 less than t1, there exists an input ut throughout this time t0 to t1. So that input ut must always be existing from time t0 to t1. This means that ut must not become undefined. Ut is defined between this time period. That means you cannot use an infinite control. That is what it is saying. You cannot use an infinite control. You have to use a finite control. It can be 0 at some instance between t0 to t1. That is fine. but this should be defined. So for an input ut between this time t0 to t1, that transfers, so we are concerned that whether an input exists so that we can transfer the state xt from xt0 equals to 0 from the origin to xt1 equals to x1. So xt is the trajectory, so this is the trajectory at any time point t, you are getting some value in this trajectory. So you are starting from t0 at t0 you are starting from 0, at t1 you are ending at x1. So this is what the problem is, or what we are trying to check from the system. We are trying to check whether there exists some input between this time t0 to t1 in which we would like to go from origin to x1. So we have a definite destination in mind, and we have a definite time in mind in which we want to reach that destination. Now the question we are asking is whether there is a control input which will take me there. By supplying that control input between the initial time and the final time, we are able to go there. This trajectory is not important, it can be any trajectory. We are only interested whether there is an input which will take me here, no matter by which trajectory. Now the system will be called reachable. This is about a state only. So we have a particular state. So for this particular state x1 we checked and we saw that yes, a control input exists. We would change this x1 to another place here, suppose x1 dashed, and we checked and we again found that there is a control input that will exist. Okay, so in this way we can check for every state x1, all the possible states, which means basically you are testing for the entire state space, right? You are testing for the entire state space. So if for every state space in the every state x1 in the state space we can reach that x1, then we call the system to be reachable at this particular time t1. So you have to fix some time t1 and then you have to frame the question of reachability, and this t1 can be any t1 which is greater than t0. Okay, so it can be just some t1 greater than t0. Even then you will be able to reach. That is what it is saying. So this is the idea of reachability. What is the idea of controllability? The idea of controllability is the reverse. It is saying that a state x0 is controllable at time t0. So it is controllable at a past time basically, because we would be moving to a future time t1. If for some finite time t1 greater than t0 there exists an input ut which is between this time, so you have to supply this input throughout this time t0 to t1, that transfers the state xt from xt0 equals to x0 to xt1 equals to 0. So here the final state is not x1, here the final state is 0. So previously you are moving in this direction from 0 to another state. For controllability, you are moving from another state to 0 in this direction. This may be from some other state, you can also try to check. Okay, so you are trying to check whether my state x0 is controllable, then you have to find out whether, so what you are checking, whether there exists a control input which will bring my x0 state to 0 in some finite time. That is what you are trying to check. You don't bother about how fast you are coming to 0 or not. You just need to come to 0. That is all. Whether there exists a control input that will take you to 0. That is what you are checking. And if you are finding that this phenomenon is true for every state x0, that means from anywhere in the state space you are able to come to 0, then you will say that the state space is controllable. Then you will say that the system is controllable. Okay, I hope you have understood the difference between reachability and controllability. Now, a point here is this: if a system is reachable, then it is also controllable. This is very easy to understand. Reachability means I am able to reach any state in the system. That means I will be able to reach the 0 state also. That means the system is controllable also. However, if I am only checked whether that I am able to reach the state 0, then I am not checking whether I am able to reach any other state. I am only specifying a particular state and happy that I am able to reach there, but I am not checking whether I am able to reach any other state. So controllability may not imply reachability all the time. However, for linear time invariant systems, these two concepts imply one another for linear time invariant systems. So this what we discussed is detailed in this slide. Basically, you can read through it, that reachability refers to the ability of an initial state to reach a set of future states. So actually what we considered as the 0 state here, xt0 as 0, this could be any initial state basically, but without loss of generality. WLOG means without loss of generality. We can take that initial state to be 0. Why? Because throughout the entire trajectory we can always subtract that initial state, and then what trajectory we will get will start from 0 state and reach a final state. That's why without loss of generality we can assume that the initial state in the definition of reachability is the 0 state, which is the origin. So it is referred as reachability basically then refers to the ability of some initial state to reach a set of future states due to some control input. Whereas controllability is the ability to have a set of initial states controllable to a final state. And this final state we have considered as 0 without loss of generality again. So it can be any final state, but we can consider that final state to be 0 without loss of generality due to some control input. So it is like this. So you have a set of states and you have a single state. So if you are trying to reach to this set of states, then you have to understand whether your system is reachable or not, reachable to this particular set of states or not. You can ask the question whether I am able to reach this particular state from this set of states. So whether this inverse relationship is true or not. That is the question of controllability. In case of LTI systems, basically in case of LTI systems, trajectories are reversible. So the path that you take to go from one place to another, you can take the same path to come back to the initial state. For that reason, reachability and controllability imply each other. So if you check reachability, you also check controllability. If you check controllability, you also check reachability. But this is not true for a general system. Please keep that in mind. Now in general, so in general means most of the time, I want to say most of the time we are interested in the controllability property of the system. Why? Because the control objectives that we have with us for any system, if you think about a system, if you think about your past course also and the laboratory experiments, you'd be able to appreciate this fact. What we are trying to do in all those, we are either trying to stabilize the system, that means come to zero, a particular state, zero, or we are trying to track a reference point, that is to bring the states to a particular value, a particular state we are trying to reach. So, and from any initial condition, the objective was to reach that particular final state from any initial condition. So this direction we were actually concerned with. We are normally concerned with reaching a particular state from any initial or a set of initial points, whether we are able to do that. So that is the question we are normally concerned with, and that is the controllability property. This I already stressed, and this is another fact that in discrete time system, controllability and reachability will imply one another only when the state matrix G is non-singular. This is a fact without proof I am stating, so you should keep that in mind. So if in the question you are given a discrete time system and you are asked whether in this system, so suppose I also tell you that this is controllable, so whether this system will also be reachable, like that a question is given. So you have to check whether the G matrix is non-singular. So if G matrix is non-singular, you can say yes, it will be reachable. Otherwise you cannot comment. Actually, if it is singular, then you cannot comment. It does not mean that it will not be reachable. You cannot comment on it. You have to evaluate the reachability also separately. Okay. Now, how to check for controllability? So do we sit and check for all the states in the state space, whether there exists a control input which will bring my system to a particular state? This is not feasible, right? Because there are infinite states in the system. So the approach is not experimental, though the definition is experimental. The definition seems to be and that the approach should be experimental, right? So we have to test for all the states possible, but the approach is not experimental. The approach is mathematical, because mathematically we can prove whether we are able to come to a particular state from a set of initial states or from the entire state space, anywhere in the entire state space. Or mathematically we can prove whether we can go to any state starting from a particular state. And actually we are going to prove the second thing, which is the reachability condition, right? We would try to prove the reachability condition, and from that we would infer whether the system is controllable or not. Okay, so just bear this in mind that the condition that we are proving is to check the reachability. So when the condition is true, the system is reachable, but we are taking the same condition to infer whether the system is controllable or not. This we can only do for linear time invariant systems and for discrete time systems where the state matrix is non-singular. Another point is this, that though we are checking for reachability condition, the condition comes in form of a matrix which we call the controllability matrix. Though we are checking the reachability condition, we are terming this matrix as the controllability matrix. So you must understand this, that the controllability matrix basically denotes the reachability condition, and because it is an LTI system, reachability implies controllability. So let us go through this. So we want to see whether the reachability is there for the system. So as per reachability definition, we can assume my xt0 to be 0. So we are starting from our state equation. Remember the state equation? We are starting from our state equation at a particular time t1. We want to evaluate the state. So at a particular time t1, we have written down the state equation. As per definition of reachability, xt0 can be assumed to be 0. Hence, xt1 is only the integral term. Nothing else. This term does not contribute anything now. So xt1 is the integral term, and in the integral term, what we have done, we have expanded this exponential into its corresponding polynomial terms, and there are infinite number of terms, as you know, the exponential expansion. So we have done the exponential expansion, and the first term is obviously I, the next term is a t1 minus tau, the next term is a squared t1 minus tau square by 2 factorial, then it will come as a cube t1 minus tau cube by 3 factorial, and so on. Now this A matrix, since it is a constant matrix, we have taken it out of the integral and written this particular expression. We have taken the A matrix out of the integral. Now consider this thing. If this particular vectors, these are vectors, B is a vector, AB is also a vector, and any a to the power of kb is also a vector. So this set of vectors, if they form a basis, so we have taken up to L minus 1, a to the power of L minus 1 b. So how many vectors are there? L number of vectors are there. So they can form a basis of L dimensional space. So if they form a basis of an L dimensional space, then the higher order terms a k b, a to the power of kb for k greater than equals to L, so these are also vectors in the same space, L dimensional space. So they can be expressed on the same basis. So the higher order terms can be expressed on the same basis. When this happens, then your xt1, which is b multiplied by some coefficient, so this will evaluate to some coefficient, this integral will also evaluate to some coefficient. So these are like some scaling of these basis vectors, and there are so many basis vectors. But what I am saying is this, that there are only L number of basis there are so many vectors, but what I am saying is there are only L number of basis vectors. Then your xt1 you can express as as a combination of those L number of basis vectors, because the higher terms a to the power of kb can also be represented or also be expressed on the same basis. Now if L is less than n, if L, so this xt1 is able to reach how many dimensions? L number of dimensions. As per our consideration, it is able to reach L number of dimensions. Now if my L is less than n, then what will happen? xt1 will not be able to reach n minus L number of dimensions of the state space. xt1 will not be able to reach the n minus L dimensions of the state space. Okay, if my L is less than n. So to reach all the n dimensions of the state space, state space, my L that I have considered here, this L must be equals to n. L must be equals to n, and that will only this will enable xt1 to reach all the n dimensions. Okay, so xt1 can now be represented, if L is equals to n, it can be represented till the term a n minus 1. You can ask, what about a n b? So I urge you to look back into the Cayley-Hamilton theorem and understand for yourself that no matter what, your an will always be a function of the lower order terms till an minus 1. You can very easily understand this. Just look back into what Cayley-Hamilton theorem says and you will be able to appreciate this fact. And once an becomes a function of terms till an minus 1, an plus 1 will also become function of terms till an minus 1. That means any function basically is a function of terms only till an minus 1. Hence xt1 is also till an minus 1. Okay. This means that the matrix formed by these n basis vectors must be full rank. So this is the final statement. So when I wish that xt1 can be any state in the n dimensional state space, then I wish that this BAB up to an minus 1b forms the basis of a n dimensional state space. That means the matrix formed by these vectors as their columns must be full rank, and the matrix formed by these vectors as its columns is this matrix called the controllability matrix. So this matrix is called the controllability matrix. Very easy to remember the formula. A bit more difficult to understand why this formula will work. Okay, so the understanding is what I try to make you go through. So you must remember why the controllability matrix needs to be full rank in order that the system be reachable. We are testing reachability, please remember that. So with this, we are very sure that if the controllability matrix is full rank, I will be able to reach anywhere in the state space. Some points to remember. This I had already stressed on point number 1, that is it used to check reachability. In general, we are interested in controllability. For continuous, these are same. For discrete time system, G needs to be non-singular. So with these points and with the understanding of reaching out to the n-dimensional state space, and for that this set of basis vectors b, ab up to a l minus 1b, their l must be equal to n, otherwise we would be not able to reach n minus l number of dimensions. So this, with this understanding, we have come to the conclusion about the rank of the controllability matrix to be equals to n, and this is what we are only checking. So we would form the controllability matrix, requires some computation. When you are doing pen and paper, it requires some computation. So a third order system, fourth order system will require some computation. So when this computation is done, then you form the matrix, controllability matrix C, and then you check whether all the columns are independent or not. And you know how to do that. Column operations, you check, you will find whether all the columns are independent or not. When they are independent, this is fine, then the system is reachable, and that means it is controllable. If it is not, then you have lost your reachability and controllability. So that is all about controllability and reachability and how to check it. So thank you for your attention. See you in the next lecture.